problem that we're looking at now is this. Given n plus 1 data points on the graph of a function, which I'll think of as being x0 and its associated function value, x1 and f of x1, and so on, down to xn, f of xn, we want to find a polynomial p of x of degree no more than n, so that when I evaluate the polynomial at one of the x values out of my data set, I get the corresponding function value from the data set. That is to say, I want to find a polynomial of degree no more than n that passes through the data points. In fancy language, we say that P interpolates the data set. We've actually figured out how to solve this problem. The polynomial that we want is the sum k equals 0 to n of the function value number k times one of these Lagrange polynomials, L n comma k of x, where L n comma k of x is the product of x minus xi over xk minus xi. For all I from 0 to n, except I have to leave the I equal k factor out, we showed by example that L n comma k of xj is Kronecker delta kj. That is to say, it's 1 if k equals j, and it's 0 if k is not j. What I want to talk about in this discussion is how you would write a program so that given a data set, you can actually evaluate this polynomial. Obviously, I'm going to need to be able to evaluate these Lagrange polynomials. Once I know how to do that, I'll combine them in this way in order to actually evaluate the interpolating polynomial. In terms of programming this, I've got a variety of decisions that I have to make. Firstly, obviously, my program is going to need to have a variable x, which represents the x that I'm going to feed into polynomial p. But on the other hand, I've got the x values from my data set also. The first thing you think of would be to have an array named x, but this would contradict the use of x in the previous way. So what I'm going to do, instead of calling the x values from the data set just an array called x, I'm going to call them x values. Likewise, I'm going to call the function values out of the data set f values. These are going to be one-dimensional arrays with indexes that go from 0 up to n, so as to mimic my mathematical formulation. And the first thing I want to do is to begin building up the infrastructure for this. I've said this before, but when you're writing code, especially if it's in a topic you're not familiar with or a language you're not familiar with, it's best to proceed in very small incremental steps. What I'm going to show you this morning is these incremental steps. I've written some programs called Lagrange, a number, and then .f90. Individually, at the beginning, these programs do basically nothing, but serve as a sanity check that I've got my syntax right. So I want to look at the first one. As I said, this program does almost nothing. Up in the main program, I say implicit none. Recall, I'm going to use x as a scalar. This is the number that I'm eventually going to feed into the polynomial p. I'm going to have allocatable arrays called x values and f values. For now, just for testing purposes, I'm going to set n equal to 2, which means in terms of the terminology of the problem, the indexes on the data pairs can be 0, 1, or 2. In this first effort, I deallocate the arrays, and that's the end of the program. It literally did nothing except allocate the memory and then turn loose of it. I have not yet written the Lagrange function, so I'm going to do what's called a stub. I've got the syntax for the Lagrange function more or less in place, but it doesn't do anything. I say implicit none. I'm not sending Lagrange any information, and the number returned by Lagrange is always 0. 0.0 in floating point, that is. If I were new at this game, I would write this, make sure that it compiles. If it doesn't, fix whatever syntax errors are there, and then go on to think about making it actually do something. So if I try to compile this, it compiles fine. There are no syntax errors. I'm not saying everything is right, but there are no actual syntactical errors in the thing, which the compiler would catch for us. So having done that, I made a second version. I'm putting these in separate files to try to be as clear as possible about what I'm doing. The first program did nothing. This program does only very little. As before, n equals 2. We allocate our memory. Now, though, I put actual numbers into x values and f values. Now, this is a very awkward, clunky way to put numbers into my arrays. Later, we'll have much better ways of doing this, but for right now, I'm just building up my program. Then I print out the x and f values with index going from 0 to n. The x numbers should be 1, 5, and 8, and the function values should be 10, 4, and 9. So I should have 2 columns of numbers, and I know what the numbers are supposed to be. Turn loose of the memory. I yet haven't done anything to Lagrange. It still always returns 0. So let me see if this compiles or not. No syntax errors. This time I'm actually going to run it because it's supposed to actually do a little bit here now. It prints out the x values and the corresponding function values. So on some crude level, I now have allocated my memory and I've brought some data in a very clunky way. In the third version of this, I allocate my memory, I set my x values and function values. Now, I'm going to make a sanity check, except it's not quite yet same as I'd like it to be. I'm going to think of these Lagrange polynomials, Ln, k, where the k can be anything from 0, 1, up to 2 in this case. For each one of those indexes, eventually I'm going to print out what I get when I stick x number I from the data set into that particular Lagrange polynomial. If you'll remember, it's supposed to be either 1 if the indexes k and I match, or 0 in case they don't. Of course, this is still not going to actually do anything because Lagrange isn't actually doing anything yet, but it will print out some stuff and let me see if I've got the syntax of my loops correct or not. Though there were no obvious syntax errors, it produced an executable, and when I run it, I get ki. Each one of those indexes can be 0, 1, or 2, so there are 9 possibilities altogether. So I'm seeing k equals 0, I equals 0, k equals 0, I equal 1, and so on. If you go down the list, you'll see that I have all the correct combinations that I'm looking at. The number in the third column is the function returned by Lagrange, which once again isn't yet doing anything. It just returns 0 as an answer. So everything that I've put in so far, I know that it's more or less syntactically correct. The compiler can't catch logic bugs though. We'll see this in a second. Let's look at number 4. Everything is exactly the same. I declare things, I allocate things, I set my data, I print it out to make sure, I go around and do my sanity check, except this time I've made an alteration to the Lagrange. Looking back at the formula for the Lagrange polynomial, what does Lagrange need to know? It needs to know the value of n, obviously. That tells it basically how many data values I got. It needs to know which one of these Lagrange polynomials that I'm talking about. So it needs to know k. It needs to know all of the x values out of my data set, which I'm calling the array x values, and it needs to know an x at which to evaluate L n comma k of x. So what I've decided to do is to make x equal to the x data value number I. If this is going to work correctly, then I should say an integer value, and then a floating point number. This floating point number should be 1 if these two indexes are the same, and it should be 0 otherwise. Meanwhile, down in function Lagrange, it now has to expect to receive n, k, x values, and x. Now, initially, Lagrange still is doing nothing, but what I'm doing is to make sure if I've got the syntax of sending the variables down to Lagrange are correct or not. Once again, functions shouldn't have side effects, so I don't want to allow Lagrange to change n or k or x values or x. So everything that's being fed into function Lagrange is going to be declared to be intent n. Any kind of information that comes out of Lagrange will be sent through the function value, which again I'm not yet actually doing. I'm just testing structure. There are no syntax errors, so I'm ready to actually make Lagrange actually do something now. So that was version number 4. Here's version number 5. Nothing has changed except the Lagrange function. Now, I've made a deliberate mistake here so as to illustrate what I mean when I emphasize this incremental development idea. Do I equals 0 to k. If I is not k, then Lagrange is its initial value, which was 1, multiplied by x minus x values I, divided by x values k minus x values I. Go around and do all of that except when I is equal to k, and return the value in Lagrange. Now, the mistake I've made should be obvious to everybody, but in case it's not, I'm going to pretend that I don't know any better. So let me save this. Let me compile this. Now, remember what we're doing. I'm taking the x values out of the data set and feeding them through this Lagrange function. I should always get 1 or 0, depending on whether or not the index k and the index I match up or not. So when I run this program, and I see, for instance, different indexes, but I've got a 1 there. The second I see that, I know something is wrong. If that's not enough to convince you, down here, different indexes and 1.75, that's a value that the L function can't take on at one of the xi's, so this tells me that something is wrong with my program. Because of the way I've been building it up, there's only one place that something could be. It's got to be in function Lagrange. So go back and look at Lagrange again. The mistake is right there. It's a typographical error. You mean to say, do I equal 0 to n, not do I equal 0 to k. There's no way on earth for the compiler to catch that, because it's perfectly legal as a programming statement. So by doing this incremental thing, I've caught my mistake, I've fixed it. In Lagrange number 6, do I equals 0 to n. So now I'm multiplying together the things that I'm supposed to be. When I run this, 0, 0, and I get 1. 0, 1. The formatting is a little odd, but the negative of 0 is 0. 0, 2, 0. 1, 0, 0. 1, 1, 1. 1, 2, 0. 2, 1, 0. 2, 2, 1. These numbers, my sanity check, these numbers are correct. So this convinces me now that my L function is working properly. We're now ready to actually put our interpolation function in. In my main program, I'm going to have a new thing, P, which is real kind equal 8, or double precision if you want to use the old-fashioned way of doing this. We allocate our memory, we put the data values in our silly way, we print the data out as a sanity check, and then I'm going to go around in a loop I'm going to check my Lagrange again. We already know it works though, so eventually we could take that out. And then we're going to check the interpolation. So I'm going to go around in a loop. I can go from 0 to n. The x value that I'm going to put into my interpolating polynomial is going to be one of the data x values. So what I'm going to do is I'm going to print out the index, and I'm going to print out the difference between f values I and what I get when I evaluate my interpolating polynomial. If things are correct, p evaluated at xi should equal f number I in the mathematics. What I should see, if this is working correctly, is the index followed by a 0, then the next index followed by a 0, until I run out of data pairs. When I look at this last bit for the checking interpolation, in this second column of numbers, if I see anything except a 0 or 0 up to a rounding error, then something is wrong, and the only place it could be wrong is in the p function, because that's the only thing that's changed since the previous go-around. Lagrange has not changed. Here's the p function. What does p need to know? On a logical level, strictly speaking, you would say just x, but p is going to be making use of the Lagrange functions, and the Lagrange functions need to know the n, the x values, and actually in the formula that we cooked up for the interpolating polynomial, I need to know the function values out of my data set as well. So what I'll send to p is n, the x values, the f values, and the x at which I wish to evaluate my p of x. How do we do p? It's the sum k equals 0 to n of function value number k times L n comma k evaluated at x. The way we do a running sum, I initialize it to 0. For each k from 0 to n, I'm going to add in the function value that goes with x number k plus the Lagrange polynomial n comma k evaluated at the x that I am feeding into the p function. So I'm just doing the sum that we said we were going to do earlier. And the thing that I'm really interested in are these numbers. We said that if things were correct, then up to rounding errors at least, that second column of numbers should be 0, which will indicate that my p of x is actually producing the correct f of x values for the x's out of the interpolating data set. So to put it briefly, this is working. The last thing I want to look at today is a slightly bigger problem. I want to make a larger data set and make sure that I still get zeros in that second column. I want to make sure that I'm not somehow fooling myself. So I've made a minor modification, which I'm calling interpolate2.f90. The only difference between it and the previous one is I've set n equal to 10 now. This means I've got indexes that go from 0 up to 10, so I've got 11 data values in both the x coordinates and the function values. Allocate your memory. I don't want to type in a bunch of numbers, so I'm being extremely lazy here. I'm going to stick a bunch of random numbers into the x values array, and also a bunch of random numbers into the f values array. Other than that, everything is exactly the same as it was before. I print out my x and f values. I do a sanity check on the Lagrange function. It may or may not be useful to look at that in detail. Previously, the indexes could be 0, 1, or 2. So when I did this double loop, 3 times 3 or 9 things were output. Here, the indexes can take on any one of 11 values, so the sanity check for the Lagrange is going to produce 121 lines of output, the last number of which should be 0 or 1, depending on whether the indexes match or not. But what I'm really interested in is whether it works or not. When this last thing is executed, I should see indexes, and if my interpolating method is working correctly, these numbers that I'm printing out after the index should all be 0. If I see something that has a little rounding error in it, that by itself wouldn't bother me any, but if I see something that looks like 1.46 or something, that tells me there's a mistake someplace. So I'll compile my program. When I run this, the 121 lines of stuff will go scrolling off the screen. If I'm interested in that, I'll run it again and make it pause. But what I'm really interested in is that thing at the end, the index and the f values versus the p of xi values. And if you look at them, I get zeros all the way down the line. This tells me my interpolation routine is working correctly. If I thought it was important to look at those Lagrange numbers, over on the Unix side, I'll run the command and pipe it through less. If you're doing this on a command line under a Windows compiler, you can pipe it through more and get the same thing. If you're doing it with a GUI, it may pause by itself, or you may have to build in pause statements. But in any case, looking at the far right column of numbers, I see ones. Negative of 0 is 0. That's just a formatting weirdness. So I see ones and zeros. Then I see another 1 when the indexes are the same down at the bottom. And I see a bunch of zeros, and then I see a 1 when the indexes are both 2, see a bunch of zeros, see an index 1 where both indexes are 3, and so on and so on. When both indexes are 10, the number that I get out of Lagrange is 1. Lagrange is acting the way it is supposed to acting. Now, I tell people that if you're not familiar with programming in general, or this language in particular, or the mathematical problem that you're solving, that it's best to build things up incrementally like this. Very often, people will just not listen to that. They'll sit down in front of the computer, start typing stuff, and then when they try to compile it, they get dozens or hundreds of error messages, and it becomes very frustrating and annoying to try to figure out what the problem is. If you will build incrementally like this, the first time you make a mistake, you'll catch it. Then you fix that mistake, and then go on to the next feature you want to put in. It may seem like this is going to use up more time than staring at the screen, trying to figure out what's wrong and hoping for a miracle, but usually that doesn't work. Usually it's a better idea to be very organized and work incrementally like this. If you do this, the whole programming thing for our Math 4670 class is not going to be very difficult.